Hi everybody. So today's lesson is on mutual inductance. So this is a new term. The word mutual implies more than one thing. So for example, if you have a mutual agreement, it implies two people, okay, or a mutual understanding, it implies two people. So similarly, the word mutual inductance involves two things. And what are these two things? Now, this whole thing about electromagnetism in year 13 is to do with induced voltage. So it has to do with how can you try and get an induced voltage, but involving more than one thing. So that brings us to a coil, and a coil is any wire that's wrapped around, let's say, a cylinder. You get a coil. It's called a solenoid, but it also has another name. They're called inductors. So inductors are just coils of wires. Okay, so let's say you've got this coil and it has some source of power. So it's connected to, let's say, a DC supply, and when you close that switch, if you close the switch, what's going to happen is that there's going to be a current through that coil. The current through the coil will have a magnetic field or lines of flux. But when the current goes around circular in this coil, the lines of flux, you're going to end up with a magnetic field or the lines of flux. Okay, so you're going to get, it's going to be kind of straight and it's going to go around. Okay, so you're going to have all these lines of flux that's produced in this coil. Okay, but if you have a second coil quite close to it, if the coil is quite far away, there's not much effect. If you have a second coil really close, so it's like two coils of wire, and one coil has got a current passing through, so around it it's got its magnetic field, and then you have a second coil which doesn't have its source of power, but what happens is the lines of flux passes through the second coil as well. So I'm going to draw a second coil. I'll just rub out this magnetic field lines. You kind of have to imagine this. Okay, so you've got a second coil of wire. And I'll just leave it like that for now. So what happens is these lines of flux also pass through the second coil. And so something's happening here, and that's what we call mutual inductance. So when the lines of flux that's produced in one coil because of a current passing through it flows in the other coil, you have what's called mutual inductance. Okay? And you'll only have the lines of flux produced when there's a current flowing. So the bigger the current, the greater the magnetic field. So this flux is actually proportional to the size of the current. Okay, so more the current, more the lines of flux. And whenever you have a proportionality sign, you have what's called a constant of proportionality. So in this case, the constant of proportionality is given by the letter M, and this M is what's called mutual inductance. And the unit in which mutual inductance is measured, so this is measured in a unit called Henry, and the symbol is H. Often you have inductors with really small mutual inductances, and it is in the form of millihenry and so on. So 1 millihenry. So 1 millihenry is 1 times 10 to the power of negative 3 henries. You just need to know that conversion. So what is this mutual inductance? It is a constant for any coil. It depends on what material is it made of, and does it have an iron core, and so on. So it's just a constant. Okay, so that's your mutual inductance. But if the current is steady, there's a steady magnetic field, so you're not going to get an induced voltage. So in order to get an induced voltage, so let's say you have a galvanometer or something here to show you that there's an induced voltage or current, or voltmeter. You will only have an induced voltage when this is changing, because in order to have an induced voltage, remember when we learnt in the last lesson, you had to be moving that magnet so that the magnetic field is either increasing or decreasing. But now you've got two coils, and in order to produce a changing flux or a changing magnetic field, there are a couple of things you can do. One of the things is you could, every time you switch on or switch off the current, if you switch the current on, if you just close the switch, what happens is the current is going from 0 to a maximum. So for that tiny period of time, there's going to be a changing flux. So there's going to be a voltage induced in the second coil. Okay, or when you switch it off, that means you're opening the switch, then the current is going from a maximum to 0, and then again there's going to be a change in current. Whenever there's a change in current, there'll be a change in flux, and there'll be going to be a voltage that's going to oppose the change. So there's going to be a voltage induced. So these are two times that you could have a change in current. There's also another way to do it. So rather than keeping on opening and closing switches, it is possible to have a source which is not a direct current, but you could have what we call an alternating current. So in an alternating current, it's sinusoidal, so it just goes up and down, up and down. So what's happening is when the current is changing here in an AC supply, the current keeps going from 0 to maximum to 0, and then it keeps going up and down that way. So if it is in this, what happening to the flux is that the flux is changing and increasing and decreasing and increasing and decreasing. So there's a change in flux that's linking this coil. So then there's going to be a voltage induced. Now there are a couple of terms more that you need to know, and that is this coil where you have a source of power, that is called the primary coil. Okay, and this other coil, the second one, is called the secondary coil. So in order to induce a voltage, you need a change in current and therefore a change in flux, and the size of this induced voltage is given by the rate of change of flux, as we learned earlier. But we just learned, I've rubbed the board, but we've just learned that this flux for this setup actually depends on mutual inductance times the change in current over time. So that's the formula that's associated with mutual inductance. Okay, so you've got the primary coil, the secondary coil, and if you know what time it takes for the current to go from one value to the other, then you can calculate the induced voltage. Okay, so that's just this lesson. It's very, very short. Today's lesson, I just wanted you to get the concept of mutual inductance, the idea that there have to be two coils. One is the primary, the other is the secondary. Change in current in one produces a changing flux, which induces a voltage in the second coil. And what I'd like you to do there are questions on mutual inductance on page 12 in your books. Sorry, yes, page 12 in your booklet. No, not even page 12, it's page 13. So there are actually 5 questions, but I would only like you to do the first 2, which is based on this formula. The next 3 we'll leave for the next lesson because it's based on transformers, and transformers work based on the principle of mutual inductance. And when we learn about transformers, you will learn actually why is it so important that we know about mutual inductance. Okay, so bye for now.